All right, so first let me say, we got not a whole lot of people in here and on the Zoom. We got about half the people. So if you're watching the video kind of after the fact, make sure you're kind of keeping up with things. If you're not attending class in person or on the Zoom, you've really got to kind of be vigilant about staying up to date with the material. And I welcome, like I said, we only have 4 people in here today, so I welcome all of you. If you want to attend in person, you're more than welcome to show up, and we'll figure out a seating thing if you're here. So let's go to where we left off, which was we were thinking about that height weight data, right? We talked about how once we've calculated the covariance and we have our standard deviations, it's just as simple as kind of plugging them into this equation, right? So take our covariance and divide it by both standard deviations. We said that gives us a unitless kind of scaled measure of the relationship between whatever our X and Y variables were. In this case, it was height and weight. So we said, 0.45, the strongest relationship is 1, the weakest is 0, so it's somewhere in the middle, right? But at least it gives us something that we can compare across different types of relationships. So if, we had years of education and income and we found a correlation coefficient of 0.7, we could say the relationship between height and weight isn't as strong as the relationship between years of education and income, right? So that's what that correlation coefficient gave us. We had a couple of these sample problems where it's really just some different numbers using a covariance and the 2 standard deviations, plugging them into this equation and calculating our correlation coefficient. So I have this link here. Based off last section, we probably won't have enough time to kind of watch it in class, but I usually like to, especially when we have more people. It's a little bit more entertaining. But it's an old Jon Stewart clip. It's pretty funny. He talks to this economist who's kind of off his rocker. It's really funny. It's a good clip to watch. So if you have time, copy and paste this into your into your web browser and give it a 10-minute watch. It's pretty funny. But really, what this economist they were interviewing, what he did was, among a lot of other things, I'll mention his most interesting kind of study, is he had these group of individuals. I can't remember the exact number of men and women he had, but they had like a LinkedIn profile to which they were applying to these jobs. So this profile had a picture, right? So every job they applied to, the company or whoever, the employer could see the picture. But for all the people that they had, they made the exact same resume, and all of them submitted the exact same resume, right? So all of the women submitted the exact same resume, and all of the men kind of submitted the exact same resume. Okay? So what they found, and then on top of this, they gave these LinkedIn profiles to like a group of, I don't remember what the number was, but like 100 random people. And they had those 100 random people kind of rank them in terms of attractiveness. And then from that, created which percentile of attractiveness each one of these people were in. Right? And what they found was, despite having an identical resume, other than the profile photo that came in through the application, you can kind of see there's a positive correlation between attractiveness and the number of interview requests for men, but there's a very steep kind of correlation there between attractiveness and number of interview requests for women, right? So this is kind of identification, first of all, that something that shouldn't be factoring in, right, to the equation about whether or not you get an interview request is, and the fact that there are differences for the genders, right? So just looking at these correlations allows us to identify some very real world problems that we then need to, create policies to help kind of prevent this, right? Making sure that, photos or something aren't kind of part of this application process, right? And he does that among other things. He talks more about in this clip about, the correlation between attractiveness and wages and salary and things like that. But it's pretty interesting and kind of shows us that a simple statistic like this correlation coefficient can actually start to allow us to see some very real world problems, okay? All right, so with that in mind, kind of wrapping up what we had left off with at the very end of last class, I'm going to post a Learn Smart when I get back to my office. That'll be due before class starts next Wednesday. So you'll have kind of, today, the weekend, and first few days of next week to just get on 10 minutes, kind of look at that. It'll be some of the end material that we'll be talking about with probabilities, but I want to introduce the idea today, okay? So you know, we say things a lot just in our common language or discussion. You know, what are the chances that some, you know, sales go, what is it, decrease here? What are the odds a new investment becomes profitable? What's the likelihood some new assembly method, you know, alters our productivity? All these statements are really getting at what's the probability that something is going to occur. Right? What are the chances? What are the odds? What's the likelihood, right? That it's really kind of interchangeable. Okay. So we're going to kind of set the framework for how we think about probability. So in order to have the probability of something occurring, what we're saying really is, look, there's some process that I don't know what the end result's going to be. I don't know what the outcome of this experiment that I'm going to run is going to be. I know that maybe I could see 50 different outcomes, but what's the probability of seeing each one of those, right? So we want to know the probability of all these different outcomes for some experiment we're running. Now, these experiments aren't like, you know, science experiments. They could be something as simple as, if I flip a coin, I don't know what the outcome is going to be. I know that it could be heads, I know it could be tails, but until I flip that coin and see what it lands, I don't know the outcome of that one experiment, that one flip of the coin. Right? If I roll a dice, I don't know what I'm going to get with this roll. I know it'll be 1 through 6, right? Unless I'm playing Dungeons and Dragons or something, or I just have a 6-sided dice. But I don't know what the outcome is going to be until I actually roll it. Right? So we're going to do is run this experiment several ways, right? The exact same experiment. So I might flip the same coin 50 different times. Oops, did something come up here? No? Okay. So I'll run this experiment the exact same way, and I can record the outcome each time I run it, right? So as I run this experiment, I'm going to start to see different possible outcomes, okay? Now, the coin example and the dice example, it's easy. We know all the possible experimental outcomes. But, you know, if I said something like, what is the average income or so, or what's your year annual income? Well, I might know the range, but I don't know exactly which outcomes I'm going to see, right? And you could think about maybe, you know, with a regular die, it's easy to know there's 6 outcomes and I know what they are. But let's say I gave you a 6-sided dice and there's pictures of animals on there, and you don't know what 6 animals are on each side. Well, you're going to run this experiment, and each time you roll, hopefully you see one of these pictures so that you start to realize what the possible outcomes are. But if I roll this dice twice, and the first time I see a picture of, I don't know, a pig, and the second time there's a lion on one side, well, if I only am able to roll the dice twice, I now know 2 of the possible outcomes. But there's still 4 other possible outcomes I haven't been able to realize because I haven't been able to run this experiment enough times, right? So the observations or the outcomes that I observe, that's my sample space. So in my example, I would have, you know, the pig and the lion picture. That would be my sample space. There are 4 other possible experimental outcomes. I just haven't seen them, right? Once we have this sample space, we then think about, we usually define events within that, right? So an event is going to be just a smaller set of outcomes from our sample space. So let's say I roll a dice enough times and I see the numbers all 1 through 6, right? But I define the event as just seeing a 2 or a 3, right? That's a smaller subset of outcomes than all the possible outcomes that I saw in my sample space. So the way we want to think about the relationship between these 3 things, you could draw this huge circle. This is every possible outcome I could see. I run the experiment, I don't know, 100 times. Here's all the outcomes that I saw from those 100 runnings of the experiment. I then define the event to be an even smaller set of those outcomes that I saw, right? So this is kind of the relative size, right? We've got every possible experimental outcome, the sample space, which might be a little bit smaller, and then kind of the event, which is going to be smaller in our sample space. So, you know, if we want to think about a couple different experiments and the possible outcomes, there's some easy ones. You know, we already talked about a couple of these. Flipping a coin, the outcomes are heads or tails, right? That one's pretty easy. Rolling a die, like I said, let's think about a 6-sided die. We could see 1 through 6. Choosing a card from a deck. If I ignore the suit, I could see 2, 3, 4, 5, or kind of ace through king, right? Every possible different face of the card. Okay? Let's say, right, Super Bowl's here in the next couple of days. So say we're playing a playoff football game, right? The possible outcomes are win or lose. Regular season soccer game, we've got win, lose, or tie, right? We could like define, you know, we've got experiments could be something as simple as this. They could be, you know, a survey question asking somebody what their eye color is, right? And recording those outcomes. So, you know, these experiments are nothing like what we usually think about when we say the word experiment. They're just something that we don't know the outcome of yet, right? We know that there are all these possible outcomes. We just don't know which one is going to occur when we run this experiment the next time, okay? Any questions at this point? Shouldn't be too bad yet. We're just kind of setting this up. So the probability, a more textbook definition, right? We're going to say what? It's the some measure of the likelihood of seeing a specific experimental outcome after we run this experiment, right? So it's going to be some measure of that. And we'll talk about different ways we can assign these probabilities. But, you know, if I think about, you know, I'll use the simplest one. So let's say I'm flipping a coin, right? I have two possible outcomes. I know they're both equally as likely. So what would you tell me, like, what are the chances that if I flip a coin, it comes up heads? 50%, right? So probabilities aren't percentages, but they're kind of the decimal form of a percent, right? So when you think about if there's a 50% chance it comes up heads, we would say the probability it comes up heads is 0.5, right? Just kind of move that decimal point 2 places, okay? So we can come up with a probability of any, you know, all these different outcomes, but if we define an event can include more than one possible outcome. So I'll try to give you an idea about why. Whoops. So if we think about the probability of an event, we should just add up the probabilities of every outcome in that event. So we did the kind of flip a coin one. If I roll a dice, seeing each number, there's 6 different numbers we could see. Each one's equally as likely. So the probability that I see, say, a 2 would be what? Just 1 over 6, right? 6 possible outcomes, all equally as likely. So the probability of seeing a 2 is 1/6. So if I define the event, and the probability of seeing a 3 is 1/6, and the probability of seeing a 4 is 1/6. If I define the event as seeing either a 2 or a 3, I would say to get the probability of that event, I just add up the probabilities of each possible outcome. So if it's the probability I see a 2 or a 3, we would take the probability I see a 2 is 1/6 plus the probability I see a 3 is 1/6, right? So the probability I see a 2 or a 3 is 2/6, right? I just add up the probabilities that are within that event, of the outcomes that are within that event. Okay? So the way that we'll start writing these probabilities is whatever experimental outcome we're interested in, E, we'll say the probability that we see that outcome is P of E, right? P, and then in parentheses put whatever outcome we're looking for. So this could be, you know, rolling a 2, seeing tails, seeing someone respond that they have blue eyes, which is the question about what color eyes they have, right? So what we know about this probability is the lowest a probability could ever be is, well, it just couldn't occur. If the chances of something occurring are that it never occurs, it's impossible, we would say the probability it occurs is 0, right? We can't have a negative likelihood of something happening, right? At the very least, if it never can happen, the probability it happens is just 0, right? The most certain outcome, or if we know something is guaranteed to occur, we would say the probability it occurs is 1, or there's a 100% chance of it occurring, right? We said probabilities are kind of the decimal form of percentages. So we know that this probability is somewhere between 0 and 1. It could be 0 and it could be 1, right? Those inequalities are still there, but it's somewhere in that range, okay? If we then add the probabilities of every possible outcome up for an experiment, those probabilities should add up to 1. So it's similar to the idea when we were making those relative frequencies. So let's do the car color. Like I could see, you know, what was the frequency that, or the relative frequency that a car was red, relative frequency a car was blue. Those relative frequencies represented probabilities, right? Which are, can we kind of think of very similar to or sorry, I think I said they represented proportions, which are very similar to kind of what we're doing with probabilities, right? And we said when we added up those relative frequencies, they should always add up to 1. The same idea here occurs. If I take every possible outcome and I take the probability of each one of those outcomes and add them up, I've covered every possible outcome that I could see, so I know that one of them has to occur. So when I add them all up, the probability is 1, right? It's a guarantee that at least one of these outcomes are going to occur. So those probabilities of every possible outcome will always add up to 1. Okay? And I'll probably give you some better visuals of this as maybe later on today and kind of next week. So we have 3 different ways of assigning probabilities, and I'll go through them quick, and then I'll talk a little bit more about each one. So we've got the classical method, the empirical method, and the subjective. Okay? So the classical method is kind of these conventional examples, like the easier toy examples, like flipping a coin or rolling a dice. It's when every outcome is equally as likely, right? So basically, if I think that I know that every outcome is equally as likely, then the probability of any one outcome, right? Let's think about it. Flipping a coin, we have 2 outcomes, right? The probability I see either a tails or the probability I see heads, it's both 0.5 or 1/2. What's the probability of seeing any one number on a 6-sided dice? I said earlier it was 1/6. What am I doing there? I'm really just taking, and I'll try not to switch because it takes a little more time, so I'm going to bear with me. We're just saying the probability of any one event is 1/the number, right, of outcomes. Man, if you can read this. So write that down, right? 1/the number of outcomes, okay? That's all we're doing with that classical method, right? So that should be pretty easy, right? But the problem is it's usually things aren't all equally as likely unless we have kind of an example that's pretty not real world applicable. Like, I guess rolling a dice is real world applicable, but like not for most everyday life, right? Or in your career. But it's still important to know if we have equal outcome or equally likely outcomes, this is how we would come up with that probability. Okay? So I can think about, let's say I flip a coin twice. The possible outcomes I could see: heads, heads, heads then a tails, tails then a heads, or 2 tails, right? 4 different combinations of outcomes. Well, if I have 4 outcomes, what's the probability that I say I get 2 heads? Just 1/4, right? 1/4, right? Every outcome is equally as likely, so the probabilities are all 1/4. Now notice, I said earlier, when you take all the outcomes and you add up their probabilities, they should add up to 1. Well, notice here if we have 4 outcomes, and each has a probability of 1/4, 1/4 plus 1/4 plus 1/4 plus 1/4 adds up to 1. Right? Also, I had someone ask last class, I don't know what situation this would apply to, but if it existed, let's say I told you the probability of seeing a heads is 1/4, and that you've used the classical method to assign these probabilities, but you only know the probability of one of these outcomes. It's 1/4. You automatically know how many possible outcomes are there. 4, right? So whatever the probability you have is 1/whatever, that denominator tells you the number of possible outcomes that there are. So you can kind of work backwards too. I'm not going to ask you a quick question like that, but it was interesting to me that, kind of thinking ahead, if you only knew, look, I've got 1/this as the probability, that denominator would tell you the number of possible outcomes that are out there. Okay? But in this case, we already knew that there was 4. So the second one is going to be the empirical method. So this is one that more likely we would use in practice. So I'll give the example, then I'll kind of explain it a little bit more in detail. So let's say I had 60 students and I asked them kind of what their favorite cuisine is, and then there's a list of options, but 15 of them kind of respond with Mexican food, right? So based off of this data, if you ask me what's the probability that any one person, if I ask them at random, what's the probability that Mexican food is their favorite? Well, I'd say based off the data, there's a 15 out of 60 chance, right? Or the probability is 15/60 or 0.25, or a 25%, if we want to say it in percentages. So I'm using some data there to assign the probabilities, right? the experiment here is a little weird. The experiment here is asking somebody what their favorite type of food is, right? But it's still an experiment. I'm asking the same question, right? Now they're different people, so I can see different responses, right? But based off the data, I would say that the likelihood that they respond with Mexican food is 15 out of 60, right? Or a probability of 0.25. So, you know, really what we're doing here, and 60 is probably a low number, but let's say, I think the example, what did I say last class? I don't remember, but let's say the question I'm asking people is what their eye color is, right? You know, unless I guess maybe I look at all the BMV records, maybe I could build a data set for the population, but let's assume I don't want to go through that process. I ask 1,000 people, random people, what their eye color is, right? I record the numbers, and maybe, I don't know what the percentages are, maybe like, I don't know, 50 out of the 1,000 had green eyes. So I'd say the probability that someone has green eyes is, what, 5% there, right? So I would probability, sorry, would be 0.05, right? So I start to use some large set of running this experiment many times, right? I asked 1,000 different people. I use that data to then assign the probabilities of seeing eye color be brown, seeing the eye color be green, seeing the eye color be blue, of asking one random person. Okay. Does that make sense? Are any questions on that? Okay. So, let's see here. All right, we're good. And the last one is subjective. Basically, somebody just has some expertise or some additional information, and they assign probabilities based off of that information or knowledge. So it kind of seems hokey, like how can you just assign probabilities like you think are correct? Well, you know, you can kind of imagine a scenario where, let's say we were hiring a CEO, and you know, you're trying to forecast who gets hired because maybe that does something different to the stock price or whatever, and you got 4 candidates, right? Well, you don't want to use the classical method. You don't want to say that each one has a 1/4 probability, right? A 0.25 probability of getting the job, because I don't know, Andy here could have like been a CEO for 3 different companies and bankrupted all of them, right? And Hill's supposed to be the next Elon Musk, right? So based off their resumes or information or knowledge we have about them, we likely know that some candidates would have a higher probability of being selected, right? Now, we can't use the empirical method either because, well, I don't have this experiment ever run before. You know, it's very unlikely we would see the same 4 candidates go up for the same CEO job ever, you know, more than once. So this is a scenario where we can't collect data and assign it empirically. The classical method doesn't make sense. So basically we're gonna, you know, I said here, an industry analyst or someone who has some expertise or knowledge in that field tries to assign the probabilities based off the information and knowledge they have about these candidates, and in this example, right, whatever company is hiring a CEO. Okay. So welcome to Probability and Statistics, a class where everything's made up and the numbers don't matter, right? You can just subjectively like assign all these probabilities. I geeked out my last section a little bit about this show, but I'll save you guys from that. But if you guys haven't ever seen Whose Line Is It Anyways, I know there's a lot more like the old clips kind of out there now on YouTube and things. You should look them up. There's some hilarious ones. I think a lot of stuff they probably wouldn't get away with today. But anyways, I digress. So we're going to dive into some notation, and then I'm going to kind of draw some things out for you to better explain it to you. But so for now, it may not be completely clear as I'm talking through this, but I'll go and I'll kind of give you a good example to match up with this. So we're going to write the complement of an event. So let's say we want the complement of event A as A superscript C. So all the complement of an event means is whatever experimental outcomes are in event A complement is every other possible outcome, right? So A complement is all the outcomes that could happen that are not in event A. We then have the union of 2 events. So A union B, or A or B, right? We read it as or, means that we're looking for outcomes that are both, we're looking for outcomes that could be in either A or they're in B, right? They could be in both, but they're in at least one of them. The intersection of 2 events, so this upside down U, or this upside down, it's really a set symbol, but it looks like a U, right? And an upside down U. So this, when it looks like a U, we said that's the union. When it's upside down, right, this is the intersection of the two events. Or we say that we read this as A and B. What outcomes are in both event A and in event B? Okay. Like I said, I'll go through an example that kind of better explains each of these in just a second and kind of write it out and kind of have a nice summary. And we'll focus on this one more next week. We'll start to talk about conditionals. So this line, right, we call this A conditioned on B. Or another way to read this is A given B. Okay? So whatever's on that right-hand side of the line, I say given that we know event B has occurred, now what's the likelihood that A occurs? Right? And we'll focus more on that one next week. Right? But for today, we'll focus on those first three. I'll switch over here. Hope it doesn't take too long. All right, there we go. I know it's a little bit dark, so let me know if you're having too much trouble seeing it. So let's say I have this event A, and I define this as saying either a 2, a 3, or a 4. So these are just the possible, sorry, I forgot to set this up. I'm rolling a dice, right? So I can see 1 through 6. Event A is defined as seeing either a 2, a 3, or a 4, right? That's kind of the outcomes that are in event A. The outcomes that are in event B, let's say 4, 5, and 6. Okay. So those are my two events. If I wanted a complement, what are the outcomes that would be in A complement? Remember, we said the complement is every outcome not in whatever event we're looking at. So every outcome not in A, which would be which numbers? If I'm rolling a dice. What was it? Yeah, right. 1, 5, and 6 are the only numbers that aren't in A. Okay. What if we want a B complement? Just these are the if these are the outcomes in B. B complement would just be 1, 2, and 3. So that's not too bad. Now, one thing I'll point out here, and maybe we'll get a little bit better of an idea at the end of class. We'll kind of push this a little further. Notice that if we took an event and its complement, we've actually seen every possible outcome. 1, 2, 3, 4, 5, and 6. We take the event and its complement, 1, 2, 3, 4, 5, and 6, right? So really, when you're looking at an event and you're looking at its complement, that should cover every possible outcome you could see. Okay? So what if I wanted to do A union B first? So this is what we said was the union, or we read it as an or. Right? So what would be in A union B? Or all the outcomes that are in A or in B? So if I look at those two events, what outcomes are in either one of them? Well, there's a 2, a 3, and a 4 in A, and there's a 4, a 5, and a 6. So all 5 of these numbers are in at least one of these events, right? Now, if there's a value that's repeated, I still only counts as one outcome, right? 4 is if I still one outcome. It's just that it happens to be in both of these two events. Okay? So A union B is every outcome that's either in A or it could be in B. Okay? What if I wanted the intersection of A and B? So what's in A and in B? What outcomes are in A and in B? Yeah, the only outcome actually that's in both of them is that value of, or that outcome of 4, okay? And I don't know why I'm using these instead of like parentheses. I think it's because this is actually similar to how we would write, like, we're not doing set theory, but they're just gonna kind of say this is the set of numbers that are in here. If you're kind of confused by that, okay? Any questions on this? I think this kind of gives a better like summary and synopsis and like has an example associated with it where it's a little bit easier to remember what complements are, what unions are, and what intersections are. Okay. No questions on that? We're okay with that? Make sure there's nothing in the chat. All right. What do I want to do at this point? I think we'll go back to the slides here. Excuse me. It's going to be ornery with me, I think, today. So let's see if this switches on the screen. Nope. Let's see if that switches our screen. There we go. Spoke too soon. All right, so another nice visual of this is using Venn diagrams, right? So let's say we draw this rectangles, these rectangles here. They represent every possible outcome, okay? So what could I think about the area of this rectangle being? If it represents every possible outcome, we said if I add the probability up of every possible outcome, that should add up to 1. So think about the space, right? Every possible experimental outcome, this represents a probability of 1, right? Because we have to see some outcome in that space, right? So if we add up the probability of every possible outcome in this space, it's every possible outcome, that probability should be 1. We'll then draw the events as circles. So here's event A, here's event B. The intersection of those two things, so what is in both of them? Well, where they overlap, right, where the events A and B overlap, that area represents outcomes that are in A and they're in B, right? So here's kind of our intersection. If I think about the union, right, the set symbol that looks like a U, A union B, or A or B, it's every outcome that's in A, or it's in B, or it could even be in both, right? So notice the union here, actually, part of the union is actually this intersection, right? Like the union includes the intersection, okay? Any questions on this? Keep going. Just kind of a nice little visual, kind of using these Venn diagrams, and I'll kind of come back to these here in a second to show you a couple other things. So the next thing I want to introduce today that we're going to be using a lot more next week are these contingency tables, right? So the way that we read these contingency tables are the totals represent the probabilities of whatever the row or column heading is. So the probability of A is 0.6. The probability of A complement is 0.4. The probability of B here is 0.5, and the probability of B complement is 0.5. So those totals represent the probabilities of just the event themselves. These top 4 left cells all represent the probability of intersections, right? So here is the probability of A and B, and that's 0.4. The probability of A and B complement is 0.2, and then so on and so forth, right? So these top 4 left cells are the intersections of whatever the row and column heading is. So I'll go down here because I have a slide, right? So if I'm thinking about the intersections, here's the slide that kind of goes along with that. I guess I kind of, jumped the gun a little bit, right? These top 4 left cells represent intersections, okay? Now, one thing we'll notice, so I told you the totals represent the probability of the events themselves. So the probability of A is 0.6. But notice if I wanted to recreate, like, where did that come from? Notice if I add across the rows, 0.4 plus 0.2 would give me that 0.6. 0.1 plus 0.3 gives me 0.4. 0.2 plus 0.3 gives me that 0.5. So I can add down the columns to get my totals, or across the rows of those intersections to get my totals. So why does that work? So I'm going to draw something for us here in a second, but I want us to remember, how am I finding the probability of A here? I'm adding 2 intersections to get that 0.6, right? The intersection of A and B, and the intersection of A and B complement. So I'm going to write that down when we go back to the white paper here, but I want us to keep that in mind when I'm about to show you. So let's go back to where I can draw some stuff for you. So I'm going to write out what I just said was true on that contingency table. We said we could get that total, the probability of A, by adding up those 2 intersections. So this is really what we were saying there, right? Take those two cells that represent those intersections, and when we add them up, right, adding across the rows, that should give you that total, or the probability of A. Need more colors. So let's say we have this space. Okay. Remember, the entire experimental outcome space, this represents an area of 1. Let's say I have event A right here. And then over here, I have event B. Okay. I can break this circle of A down into two components. So the first component I'm going to break it down into is this part of circle A. Right? Well, what does that area represent? Outcomes that are in A and B, right? They're both in circle A and they're in circle B. So really, that area represents the probability of A and B, right? The intersection of those two. Now, this is where it gets a little bit tricky if you're trying to recreate what I'm drawing. But where would B complement be? Well, here is circle B. B complement is just every outcome not in B, right? So imagine that this is shading and not just straight lines. It's a little bit harder for me to shade with a Sharpie marker. So when I say the shaded area, it's really these lines I'm drawing that represent, right, B complement, everything not in that circle B. Okay, so let's return then to the other area of circle A. Notice this area of circle A is everything, every outcome that's in A, but not in B, right? Or it's in A, and it's also in B complement, right? That shaded area represents B complement. So where B complement intersects with circle A is just this red area. So that's the probability that I'm in A, and I'm also in that black shaded area, which represented B complement. So notice if I add these two components up, that would just give me all of circle A. Well, if I add up these two components, notice it's exactly what I was saying with the contingency table. These two things should add up to the probability of A. Okay? Does that give you the visual, make a little more sense what that would hold? But that's why we can add across the rows and then like down the columns. Think about it this way. So the probability, if you think about what's the probability? I'm thinking about something. I was going to do something with weather, but now I'm thinking. So what's the probability that you get in a car accident, right? That's event A. Well, it's the probability of getting in a car accident and it's raining outside, plus the probability of you getting in an accident and it's not raining, right? Because raining and not raining, you just covered every single possible scenario. So when I add those up, I should just have the probability that I get in an accident, right? But I can break it down into two components. When I add those two components up, that should cover every possible time I could get in an accident. If we think about getting in an accident as event A, I guess that one's kind of morbid or not very good, but hopefully this kind of helps cement the idea. So before we go back to the slides, I do want to show you one more thing, just because there is a delay when we switch. So any questions on this before we keep moving? We're okay with this? Check the chat. All right. So one thing that I'll point out when we go back to the slides on the contingency table, but if I think about an event, so here's every possible experimental outcome, and here's event A, okay? Notice, if I think about A complement, it'd be this like shaded area. So the shaded area is A complement. If I take event A and I add to it A complement, I filled out every single possible outcome that I could see, right? So if the area, we thought about the probability of all the outcomes add up to 1, really what I'm saying here is if I take the probability of A and I add to that the probability of A complement, those two things should add up to 1, right? It should fill out the entire experimental outcome space. In fact, when we had that example earlier, we thought about all the outcomes in B plus all the outcomes in B complement, that covered every possible outcome. So when you add the probability of an event and the probability of its complement, you add those together, you'll always get 1. And that should cover the entire experimental outcome space. Okay? Any questions on that? So what we'll notice is, and I had to switch this for us in class here real quick. If we go back to the contingency tables, so if we're adding across the rows, we're adding up those 2 intersections to get the probability of the event itself. Once we have the probability of A and the probability of A complement, hopefully those add up to 1, otherwise we made a math error, right? Because the probability of an event and its complement, that should fill out the entire experimental outcome space, those should always add up to 1. Sure enough, down here, probability of B and B complement, those will add up to 1 as well. Okay. I think I have, do I have one with different numbers? No, these are all the same numbers. So go back here. You know, so those totals, you know, probability of the event and its complement should always add up to 1. We talked about adding across the rows, down the columns. We talked about these top 4 left cells all represent the intersection of the row and column heading. All right. So if I ask you a question like this, what's the probability of R1 and C1? All you should have to do is what? I want the intersection of these 2 events. So which of these cells represent intersections? Just said not too long ago. The top 4 left cells, right? These cells represent the intersection of their row and column heading. So the probability of R1 and C1 should be what here? 0.4, right? Probability of R1 and C1 is in this cell, and that's 0.4. Okay. What if I asked you for what's the probability of R2? 0.4, but not this one, right? You went over, you looked at the event R2, and you went over the total count, right? I think because the other section we left, we didn't get to cover this, so I think I'll just pick up both of you on the same page. But next week, we'll revisit these contingency tables. We'll talk about how we can use them to find unions, a couple different ways to find unions. We'll then start to talk about, where was it? Here it is. How we find the probability of conditional probabilities, or these given, A given B. And just kind of continue on with some more probability work. So I know that this is kind of a harder subject. It starts to get into stuff that sometimes people start to first like hitting a roadblock with. So I'm trying to work through it slow, kind of give us a really good base for probability, because we're going to push it pretty far. Okay. Like I said, I'll get that Learn Smart up there. That will hopefully help kind of prime our brains for next week's discussions. You've got that Excel and Connect homework, which are both due by the end of the day next Friday. So just about a week left to do those. I've had a couple people kind of email me. I met with 1 or 2 people via Zoom. So if you have questions on those, make sure you get those out of the way early. Feel free to reach out to me and I can kind of help you with those. Other than that, any questions from me before we kind of get out of here? I promise you, if you use that link and watch that old Jon Stewart clip, you won't be disappointed. It's a little bit longer than kind of we have left in class. So, yeah, if there's no questions, start tackling those homeworks, and I'll see you guys on Monday. Like I said, not a lot of people here, so if you want to attend in person, feel free to show up. Other than that, have a good, safe weekend.